Our next speaker is
Schou Gjaldbæk.
Thank you.
You're welcome, and thank you for organizing this, and thank you for inviting me to talk. The title of my talk is, as you can see, Classification of Quadratic Packing Polynomials on Sectors of R2, and this is joint work with Madeline Brandt. So I will begin with a short introduction, and then I will present the main result of a paper we put on arXiv, and give some hopefully good examples, and then if time permits, I'll sketch our proof. So to begin with, let me define. If you have a countable set I, we call a bijection from I onto the non-negative integers a packing function on I. So as an example, if you take any positive integer, you can write it uniquely as a product of a power of 2 and an odd number. So the function you see here, f of x comma y equals 2 to the x times 2y plus 1, and then minus 1 because we want to include 0, is a packing function on n naught cross n naught, so n naught representing the non-negative integers. If this happens to be a polynomial, which the example isn't, but if a packing function is a polynomial, we call it a packing polynomial. So the first of its kind is due to Cantor, which is the polynomial you see here. And he mentions in 1878 paper that this function has the remarkable property that it represents every positive integer exactly once when you let x and y run over the positive integers. A little later, it was studied in more depth by Futer and Polya. So one of these two polynomials, f and g, is obtained from Cantor's polynomial by translation to make it go from n naught cross n naught into a naught. And I can't remember which one it is, but it's one of them, and the other is obtained by swapping the axes. So if you plot the function f, you get, these are the values written in the coordinates. If you have x out here and y out here, you get the function values, and you see, or it's easy to be convinced at least, that this is indeed a bijection onto a naught. And I drew these diagonal lines so you can see that when you go up along these diagonals, the function value just increases by 1, and the next diagonal picks up exactly where the previous one left off. So this is f, and g is then similar, just counting downwards. Futer and Polya, they proved that these two polynomials are the only quadratic polynomials that have this property. And they conjecture that it is impossible for higher degree polynomials. Still an open problem, but a little bit was done in the 70s by Liu and Rosenberg. They studied the problem in more generality, came up with proving the degree 3 and 4 case that it's impossible for a packing polynomial in these situations. Now jump to 2003. Melvin Nathanson puts a paper out where he studies the more general situation of, instead of looking at the lattice points in the first quadrant, you look at a sector that is between the x-axis and a line through 0, 0 with slope alpha. So we define this sector as S alpha and the lattice points inside it as I alpha. And just so that we can refer to the original case, we call that S infinity or I infinity. In the, so here's a picture of a sector in case you couldn't visualize what it looks like, there is indeed a line with slope alpha, and I've dotted out the lattice points for your convenience. So in the paper for certain sectors, Nathanson solves everything there is to solve. So if you take a fraction of the form 1 over m, where m is any positive integer, these two polynomials are the only two quadratic polynomials on the sector. And here I've plotted as an example with alpha being equal to 1/3. I've drawn these lines, these straight lines, that reveals that something very similar to what happened before is going on. If you count along those lines, you see that the function value skips by 1 every time. And when you move to the next line, it starts exactly where the previous picked up. And this was f, and g looks quite similar, except the counting just goes in the other direction. And I call these the Cantor polynomials in quotation marks because they are exactly obtained from the Cantor polynomials by a transformation of the lattice. So this transformation is invertible, and it takes all the lattice points to lattice points inside our new lattice. So every result on sectors of the form alpha equals 1/3 or equals 1 over m can be obtained from results from the original problem. If you look at sectors with alpha being an integer, these sectors are not equivalent to the original problem. And Nathanson comes up with two polynomials for each such sector, f and g. And if we plot, here's f on the sector with alpha equals 3, you see that something similar is going on still. So when you move along here, the vertical lines, you see that the function value increases by 1, and the next line over, again, it picks up exactly where the previous left off. And if this is the picture of f, g is just counting in the opposite direction. So the paper ends with a list of problems. For one, the question of, are there any packing polynomials on sectors with an irrational alpha? The question of whether there are packing polynomials on higher degree on sectors. So this is the future and Polya conjecture just restated for sectors. And then classify quadratic packing polynomials on sectors with rational alpha. And these questions are not all solved. The first I solved in my thesis. So this I proved in my thesis, and this was also the subject of the talk I gave last year. In the quadratic case, it is impossible to have a quadratic packing polynomial with a rational alpha. The case of high degree polynomials is still open, sector or no sector. And the subject of the paper I wrote with Brandt is the classification on rational sectors. So the first progress was quite soon after the paper came out. Caitlin Stanton proved that if you have a quadratic packing polynomial on a rational sector, the quadratic part of the polynomial must have this very specific shape depending on the number alpha n over m. And it is it's known that the coefficient of y squared must be a half integer. So it immediately becomes a necessary condition that n divides m-1 squared. Now, this allows us to rule out a lot of rational sectors immediately. For instance, there can be no quadratic packing polynomials with alpha equal to 3/2 because 3 doesn't divide 2 minus 1 squared. So the the integral case was also solved by Stanton in the same paper. I wrote 2015. This is the same paper. That should be 2014. Sorry. She proves that the two Nathanson polynomials given before that come with any integral sector are the only two packing polynomials except for the two cases alpha equals 3 and alpha equals 4. In these two cases, we get two additional polynomials. And these two additional polynomials have a bit of the same flavor. Here are the two on S3. So you see, when you move along the vertical lines, you don't go up by 1, but you go up by 3 instead. And you have, of course, since you skip by 3, everything on a vertical line is in the same congruence class mod 3. So what happens here is when you reach the top, you go to the next line that has the same congruence class, and it picks up exactly where the previous left off. And for alpha equals 4, the jump is by 2 instead of 3. So for the remaining rational cases, Madeline Brandt puts a paper on arXiv where she essentially gives a complete solution to the problem. This is the polynomial as it must look if it is a quadratic packing polynomial on a rational sector. Now, the number L is the greatest common divisor of m-1 and k is the, I just call it the jump integer here, which is 2 in this case and 3 in this case, or -3. And in all previous examples, it was plus or minus 1. And she also determines exactly which rationals allow for quadratic packing polynomials and specifies the value of k. The article was incomplete and remained in preprint. In my thesis, I ironed out a few creases to the satisfaction of at least my thesis panel, and I contacted Madeline, and together we wrote an article that we put on arXiv. And this is the main result of that article. So if we have a rational sector given by n and m co-prime, you put L to be the greatest common factor of m-1 and n dividing the square of the greatest common divisor is equivalent to Stanton's necessary condition that n divides m-1 squared. Now, if you have any of these conditions, you get the following quadratic packing polynomial. Now, multiple can occur. Anytime you have a congruence, you can set k equal to, it has to be the same sign. So I'll show in a bunch of examples exactly how it works. But let's just notice first that so far we've seen sectors where we had two packing polynomials. It was all packing polynomials with k being plus and minus 1. And then we had the two additional ones, plus and minus 2 and plus and minus 3. So we've seen sectors with 2 and sectors with 4. Now, this shows immediately that there can be no more than 4, because there are only 6 different congruence cases, and 2 and 3 can't happen at the same time, because the number L squared over n can't be 4 and 3 at the same time. So you can get 2 or 4. You can fiddle with congruences to convince yourself that you can't have exactly 3, but you can have exactly 1. As in this example, if you consider alpha being 9 over 7, then the greatest common divisor of n minus 1 and n is 3. L squared over n is an integer, so this is the necessary condition, and it's 9 over 9, which is 1. N over L is 3, and m minus 1 over L is 2. So the congruence 2 is congruent to minus 1 mod 3 holds. That means we're allowed to set k equal to 1, sorry, minus 1, and this gives us a quadratic packing polynomial. Now 2 is also congruent to 2 mod 3. But this is where we had the extra condition that L squared over n would have to be equal to 4, which it isn't, because it's equal to 1. So for alpha being 9 over 7, there's only one quadratic packing polynomial. And this is what it looks like. And if you, lines a little closer here, but if you follow one of the lines, you can see that k just does go down by 1 when you go from one lattice point to the next. Now, here's a different example. If n over L equals 1, so this means n divides m minus 1, and note that this includes all cases with alpha being an integer, well, then all the congruences are trivially true. This means we can set k equal to plus minus 1. That works. And then for the cases plus minus 2 and plus minus 3, we note that L squared over n is equal to n. So we get the 2 additional when n is equal to 4 or n is equal to 3. And this recovers Stanton's polynomials. Now, Nathanson does actually discuss sectors where n divides m minus 1 in the case k equals plus or minus 1. These cases are all equivalent to integral sectors. Here is the k plus 1 polynomial with alpha equals 4, and a similar transformation as the one we saw earlier shows that this is equivalent to the sector 4 over 5, and we can continue. It's also equivalent to 4 over 9, 4 over 13. You can keep adding 4 to the denominator. In the case n over L equals 2, the number m minus 1 over L is always congruent to both plus minus 1 and plus minus 2. So we can always set k equal to plus minus 1. Now, in the plus minus 3 case, we need L squared over n, which is n over 4, to be equal to 3. Solve for n, you get n equals 12. Now, if n over L is 2, L is 6, so this means m minus 1 must be congruent to 6 mod 12. In these cases, we get 2 additional quadratic packing polynomials with k being plus and minus 3. Now, these were discovered by Brandt in the first paper she put out. And this is what the plus minus 3 polynomials look like. And you can see that they do go up by 3 or down by 3. Okay, so let me quickly sketch the proof. We start with ruling out irrational alphas. So we can, this is just referring to a previous result. And then our starting point is essentially Stanton's result, which said that n has to divide m minus 1 squared, and the quadratic part of the polynomial must look like this if it is a quadratic packing polynomial. Now, the linear terms are half integers, so d, e, and f must be integers, and for reasons you don't have to worry about, I'm subtracting the coefficient of x squared and the coefficient of y squared. It's not really important. So the important thing is the observation that on the quadratic part is constant on lines with slope n over m minus 1. And these are the lines that we've been looking at all along. So these are the lines we follow where this quadratic polynomial is actually linear. If we factor out the greatest common divisor, then we can chop up the lattice into points that lie on straight lines so each lattice point will be on one of these lines for some unique I. And if we restrict the set of lattice points to the sector we're interested in, we get a finite for each I number of points that we call the ith staircase. And together, these all make up the lattice points in the sectors. Maybe a picture is more convincing. So these are lines Li and restricted to the sector, and only taking the lattice points, we get the staircases Ji. So if you evaluate the polynomial on two consecutive stairs on such a staircase, the difference between them is constant. And this constant depends on D and E, but we just call it K. And this is where that K comes from. So it makes computations a little bit easier if we perform a transformation that's similar to the ones we've seen, with the difference that this upper right entry is not an integer. So the skewed lattice is not necessarily an integer lattice. And same goes for the staircases. But we can still talk about quadratic packing polynomials on the transformed lattice and carry over results to the lattice we started with. And the benefit of this is that when we look at the polynomial on the transformed lattice, we get this nice form where we see that all the terms with y disappear in the quadratic part. And this essentially means that the staircases before all turn vertical. So we start with assuming that k is greater than 0, and then some lemmas can allow us to write d in terms of k. So remember, e was hidden somewhere there in k, so we're just eliminating one term really here. But it leads to this nice improved necessary condition. If you have a quadratic packing polynomial on the transformed lattice, it must look exactly like this. And this is good enough to give us a sufficient condition if we let y hat I denote the y coordinate of the first step on the ith staircase, then the set of values of p on the first steps of the first k staircases has to be 0 up to k minus 1. If this is the case, then the formula shows everything will fall into place. And then we can again use this necessary condition. If you add up all the numbers from 0 up to k minus 1, you have a nice formula for that. This is k minus 1 times k over 2. And this you can add up and you get some expression on the left-hand side, you get some equation, you can solve this for f, and you get this expression for f. And then you simply test all cases. So this imposes some strong restrictions. First of all, you see if k is equal to 1, this is 0. And the necessary condition in the case k equals 1 is just that f of 0, that p of 0, 0 is 0, which it is. So when k is 1, in this case, you get, that's why you get, when k is 1, you get no further restrictions. You put in 2 and 3 and fiddle with it a little bit, and this L squared over 2 becomes forced, and that's where you get these L squared over n. Sorry, did I say L squared over 2? L squared over n equals 4, and L squared over n equals 3. That's where you get those conditions from. And move a little further, you can rule out k being greater than 3. And finally, we can show that the negative k cases correspond to a sector with a positive k. So this picture shows how that correspondence is, and that the sectors are not always the same. So here, if you look at alpha being 9/4, you do the sector transformation. Now you can flip the staircases on their heads by another transformation, but this doesn't fix the transformed lattice. So when you move back to an integer lattice, is not necessarily the same as the one we came from. So this was the example we had for where k was equal to -1. So this is equivalent to the case where alpha is 9/4, and in this case, k would be +1. And that is the end of my talk. Here are the credits.
Okay.
Thank you for your time.
Thank you very much, Kurt. We have to go straight to the next talk.